So good afternoon. So starting a new talk in this series of industrial talks. So today we have the pleasure to have Paulo Augusto Dal Fabbro from Chipus, but in this moment he is not in Florianopolis, he is now in Switzerland. So he's talking directly from Switzerland today. So Paulo Fabbro has obtained his undergrad and master degrees in the State University of Campinas in Brazil, and the PhD in Microelectronics in the École Polytechnique Fédérale de Lausanne, Switzerland. And during his PhD studies, he has the opportunity to work in cooperation with Fujitsu Labs in Japan and with EM Microelectronics, that is a Swatch Group, belongs to the Swatch Group in Switzerland. He is also co-founder of Chipus Microelectronics, that is based in Florianopolis, Brazil, where he acts as CTO, and he's currently SVP of Operations at Chipus, and he's based in Lausanne, Switzerland, so in the border of a very nice lake. So thank you very much, Paulo, to accept our invitation. So the floor is with you. We have also here the participation of Heider Marconi, that also will be available for the questions after the talks that will be done by Paulo. So thank you very much, Paulo. So the floor is with you. I'm going now to pass you the control of the presentation. It is done. But before that, I'm going to switch for your slides. Just 1 second.
Okay.
So it is done.
Yeah.
Now you have the control of the presentation. So thank you very much again.
Perfect. So thanks a lot, Professor Ricardo Reis, for the introduction. And more than that, for inviting Chipus to be present here today. Even if it's an online event, we are not physically present for this talk, but it's a pleasure to be here today to discuss a little bit about ASIC flow, and it's an honor to have received and been able to accept this invitation. So as I said, as Professor said, I'm talking from Lausanne, Switzerland, so I'm 5 hours ahead of Brazil. It's 11 o'clock in the evening here. So I will begin. So I'll talk about the ASIC flow from concept to product. This is the title of the presentation. And to do that, I outline my presentation as follows. I will start with a motivation, why we do ASICs in the first place, and then start talking about each step in the ASIC flow, starting from the concept, an idea to develop an ASIC, then go to the phase of capturing the specs or to develop a feasibility study if it's necessary, and then starting the design of the IC. After that, the IC must be fabricated. There's some post-processing steps on the wafers so that they can be made in a form of a die, which then has to be packaged so that we can access the terminals of the internal terminals of the chip to do the tests in the lab or in production. And then we go to our qualification phase, and then finally to production. This slide shows all those steps from concept to production, and I will use it throughout the presentation to guide me and you as well during the whole presentation. What is an ASIC? When an ASIC is a solution? I will answer these questions in the sequel, and then I will talk a little bit about the business engagement model. The definition of an ASIC can be found in several places. I took one from this book that I recommend. It's called Understanding Fabless IC Technology. And it states that the ASIC industry started in the early 80s. And it was a way for companies, specifically system companies, to access design tools and semiconductor technologies to be able to implement application-specific devices without the need to invest in the semiconductor business itself. This enabled the companies to focus on what they did best, which is focus on their customers and specific market needs, and led to the ASIC suppliers to be the experts in the design and the manufacture of semiconductors. Then we have also the fabless ASIC model, which goes a step further and utilizes an outsourced approach in several steps in the ASIC flow. There are some terminologies that are used in this industry, and I will go through them just for the sake of clarity. First of all, there are the standard ICs, there's the standard integrated circuits, which are the off-the-shelf components that we find in companies or in stores such as Mauser or DigiKey, or in an electronic shop near your place. These are the analog devices type of components from TI or from Maxim, from several of the makers that we know. Then we have the ASSP, which stands for Application-Specific Standard Part. These are custom chips that are designed specifically for an application, but they serve multiple customers. And then we have the ASIC, which is the topic of our presentation today, which stands for Application-Specific Integrated Circuit. And this is a custom chip that's designed for a single customer. And all of those circuits can be of several types, like a microprocessor, can be an FPGA, can be an SoC, which is a system on chip that in general contains a microprocessor, but that means a circuit that's complex and has several parts, several blocks, digital, analog, several peripherals inside the chip. You can also have chips developing or performing the functions of a sensors or some basic functions like voltage regulation or A2D and D2A conversion, for instance. And why ASIC is a solution, or when ASIC is a solution? Of course, it's not always, but there's sometimes that is interesting to have ASIC as a possible solution for the product that you're a company, a system company or a fabless company is developing. And this happens when the standard IC, the off-the-shelf IC or the ASSP is not available. So it's a new functionality that's being looked for, or it's too expensive because it offers much more than the application needs. So it has features that are not going to be used, but it's the only thing that you have in the market, and you have to live with it. So it will be too expensive for your application, or the performance is not good enough, and you need to improve the performance. Or you have an IC that's going to obsolescence, and you continue to need it, to require it in your product. And instead of redesign all your products again, all your boards, or everything, maybe it's better to develop an ASIC to replace that obsolete part. And what are the benefits to have an ASIC? Some of them I already said, like to improve the performance. You can also reduce the power consumption by doing a diligent design and looking for squeezing the power consumption everywhere you can. You can have a reduction of size by integrating parts of the components that are on the board, or reducing your bill of materials, and put all those things inside the chip. Of course, you have to check if it's feasible or not. You also get an improvement in IP protection, which means that your competitors, if they want to copy your product, they have to enter inside the chip to understand what is there, and not just look at the board and see what components are there. So it's much more difficult. You can add new features that are specific for your application, and you can also suppress useless features in order to reduce size, cost, or make it a linear product. And of course, you can also reduce cost. Yes, you have a cost for the NRE that we'll see later to develop the ASIC, but at the end, the unit cost for each of the chips that you're going to buy can be reduced by doing an ASIC. And what does how does a customer engage, and what does the ASIC customer pays? He'll pay for the ASIC company. In our case, Chipus would be the ASIC company. NRE, which is the non-recurring engineering, and this is a fee or a price or a cost that will cover the design of the ASIC, the IPs that are going to be used, in internal IPs or third-party IPs, the mask sets used to manufacture the wafers, the prototypes or engineering lots, the test hardware and software, and all the tooling that's necessary for all the phase of the wafer post-processing. This is just the NRE. Besides that, of course, the customer will pay for each ASIC unit that it buys, it acquires in production. Now, finishing the motivation part of the presentation, start each step of the ASIC flow, starting by the concept. So the concept can be different depending on the ASIC type that the customer wants. So maybe it's a completely new ASIC from scratch, or it's an adaptation of existing IC, but to a new application. So you have to add or remove features, you have to change some parameters. You want to increase performance, reduce costs, or increase the IP protection. You need, for instance, a pin-to-pin compatible, as in the case of to replace obsolete ICs. You can also do an FPGA to ASIC conversion, for instance. In case where the FPGA is also becoming obsolete, then you can do. We have had one example of this in our company. And examples of how this concept comes to us as customer inputs. The customer can come with a complete specification. This is very good and can be refined during the design, or just a block diagram with some ideas, or just an idea. I want to do something, but there's no formal or more detailed description in terms of specifications of the ASIC. Then we start what we call the request for quote or RFQ process. So we receive an ASIC request from the customer, and we ask ourselves several questions to check if we will continue or start this project if everything goes again in the negotiation. But we ask some questions like, are we able to do what the customer wants? Can we establish or use strategic partners to help us in this endeavor? Do we have IPs that we can reuse to make the design easier, to reduce cost, to reduce time to market, to reduce risk? So based on several questions that we ask ourselves, sometimes we have a no, and then we can redirect the customer to do that ourselves for some reason. Or if it's a yes, then we are starting to prepare the proposal, go for a negotiation with this proposal to the customer, then do the contracts, and then start the project. So this is where finishes the concept. And then we start the project inside of the company. And it starts with the specification phase, or sometimes with a feasibility study phase. So the feasibility study is, sometimes it's already done by the customer. Sometimes it can be merged with the specs capture. Sometimes it has to be done before the specs phase, because it's something that we have a less idea if it's feasible or not, so a formal feasibility study may be required, or even you need to have a proof of concept before starting that. Sometimes you need to prove that, like with discrete components, for instance, to prove that the concept is valid, and then you can then think about making an ASIC out of it. So there are all those types of feasibility studies that can be done. And when you enter the specs capture phase, then you're going to define or refine, depending if you already received the specifications from the customer, all the electrical parameters for the circuit, the features, the operations, the modes of operation. You will choose the foundry and the technology within that foundry, and this is related to technical aspects and also to cost aspects. You're going to decide about the package. You're going to decide about the circuit architecture, which architecture is best for that for the constraints of the application, or design, or costs, or all of them together. You're going to procure third-party IPs and reuse internal IPs, and then maybe you need to port or retarget internal IPs. You're going to refine the schedule. The schedule was already, all of those parts here were probably already part of the proposal that was negotiated with the customer, but this will be refined during the specs phase, or the specs capture phase. So the schedule will be refined, and in the end, in the output, you have an IC specs document, a formal document with all those things that can be used afterwards to verify if the ASIC is okay, if it's working according to the specifications. Then, talking about the IP reuse, this is something that is very interesting and important, because when you reuse IPs, you can reduce time to market, or the design time. You can reduce cost, because you don't have to spend engineering time to redesign those IPs. Maybe you have to retarget it, so there will be some customization, and also maybe some porting, because not all IPs are available to all technologies, so you have to port it to another technology or to another foundry. And you can reduce risk. This is very important, because if you have that IP that's already silicon proven, it was already tested, even if it's another technology or with some other different specifications, you reduce the risk, the technical risk of the design. And this is very interesting. So at Chipus, we have plus than 200 IPs in our portfolio, and this helps us a lot in scoping the project in the first place, but also being able to achieve aggressive schedules and costs that comes to us as requests from our customers. Then, after this specs phase, we start the design. That's the interesting part for the engineers that are watching this talk today. This is the fun part. That's the design, but it's also that has its challenges, of course. And it begins by revising the specs and refine the specs for the sub-blocks of the system. And then the design itself, analog or digital or both, with the very well-known flow, like schematic entry. You do the simulation using commercial EDA tools. Then you do the physical implementation or layout. And then you do post-layout verification to be able to extract the parasitics, and you verify after the parasitic extraction. And then you have the top level part of the design, which is the integration both in the schematic and layout levels, and also the top level verification. And of course, you have the counterparts for the digital codification, verification, the backend, and then the things that are in common, that are the post-layout verification and the top level verification. And before going to tape out, you also have to work on the test plan, because you don't want to have taped out a chip and then discover that you're not able to test for some reason because you forgot to an access to a certain part of the circuit that you want to test, or you forgot a buffer to be able to measure a sensitive signal. So all this has to be sought before the tape out, during the design phase. And then you go to the tape out, you send the GDS to the fab, to the foundry, and this is a very important milestone in the ASIC design. And all those phases are go in parallel with documentation for the design, for everything. Checklists for tape out to be sure that you have done the job correctly, and reusing lessons learned from previous projects to avoid incurring the same errors that you might have incurred in the past. The management, which is always going on from the start to the end of the cycle, and communication, which is of utmost importance, because it is where you put the customer and the provider on the same page. The communication must be very precise and frequent or regular, and the communication must happen inside the design team, inside the company, between the companies, and it has to go all the way through the end of the ASIC flow. And of course, you have challenges, and the challenges are IC design. By definition, is a complex matter, so it has the challenges by its own. But you have specific challenges like ultra low power design, when sometimes you need to squeeze the power consumption, and you have to choose ultra low power techniques that are challenging. But we have a good background in Florianopolis due to the proximity to the local university, the Federal University, that has a very good and renowned lab. So lots of our engineers comes from them with this background of ultra low power design, and a methodology for mixed signal verification, which is also very, very important, and the capacity or the expertise in integrating everything, because designing a block is one thing, designing a whole chip is a completely different thing. There are lots of interactions between digital and analog, between sensitive signals and switching signals at high speed and high power. So all of this require expertise and good tools in order to be able to deliver a good ASIC at the end. So in the analog design, you do some behavior modeling, device level simulations, layout implementation, physical verification. Then you have a smiling face at the end that makes every designer happy. And there's nothing specific about it, but it's part of our job. It's part of the design flow, of the ASIC flow. And of course, every analog design is challenging. There is risk involved, so that's why it's very good to be able to reuse IPs, so that you minimize the risk of new circuits being implemented. But of course, we are always developing new circuits, and we are always improving our expertise. Not just as Chipus everywhere is like this. And then we have the design. The digital design. The digital design has also its specific flow coming from the design itself and function verification, to the logic synthesis, to the structural verification and the design implementation. So starting the RTL modeling, RTL, then the logic synthesis and the STA analysis, then place and routing. All those things are performed throughout the digital design. That of course has its own challenges, It's not my specific domain, digital design, but we have a very good team at Chipus that's doing a very good work. Although Chipus was born not as a digital company, a digital design company, we were born much more as an analog company, but we now have a very good qualified team doing digital design for us, as well as analog team, of course, and also the layout team. And the mixed signal verification, as I mentioned, it's an important part of the process, because you have to deal with all those interactions between the different parts of the circuit, and besides that, you have also to know how to use the tools to be able to really simulate the circuit in its completeness. Sometimes you need to use some abstractions, like using parts of the circuit as behavioral models to improve the simulation time. Sometimes it's not feasible to do all the complete chip in a device level, so you have to use different simulation engines, and this has a lot of expertise involved, and it's an important part of the process. After you design and you tape out, you go to the IC fabrication, and the IC fabrication itself has also different aspects that must be taken care of, so that you can choose the right foundry and the right process for that particular ASIC. So technically, you can choose different types of process, like a CMOS process or a BCD process, depending on the requirements of the ASIC. You will check the available devices, the available IPs, and a lot of things that must be looked at in technical terms to define the technology. Of course, you might want to reuse the technology that you have already expertise, and this is something that's very important. So if you are able to use the same technology that you have already used in the past, you take advantage of the lessons learned from previous projects. You know the devices, you know the behaviors, you know a lot of things. So it's very good to repeat. But sometimes you cannot use the same technology for other reasons. One of the reasons may be cost, for instance, because if you can just decide technically, it's one thing, but sometimes you have to also manage the cost part of it. So in the cost part, you have to take care about the NRE. Here again, there's a non-recurring engineering, which is the price of the MPW or the engineer lots or the mask sets, and the wafer price in production. So this you have also to choose this based on the constraints of the ASIC business that is in place. And also the schedule is an important part, because there is the fabrication cycle time. An MPW, for instance, can take 3 months to 4 months, and a dedicated mask, even if it's a multi-layer mask or a full mask set, can take maybe two months, for instance. So this is important when you are deciding about the schedule. Sometimes the schedule is very tight, so you need to decide also based on that. You can also count on priority lots if the schedule is very tight, and for a premium you can have a better cycle time. And the technical support, which is very important, because sometimes you need specific demands for a particular design. Sometimes you need to verify or to a model for a condition that it's not on the manual or on the characterization that the founder provides. So we might need specific characterization, and not all founders will be able to support this. Mainly the big founders will support the big customers, but the small customers, they probably will not support for this specific kind of things. And then you have also the wafer physical characteristics, the thickness. In general, the wafer comes with a thickness of 725 micrometers, and then you maybe have to back grind it, depending on the need of your application. And the diameters, industrial diameters that you have today are 8 inches or 200 millimeters, or 12 inches, 300 millimeters. We have also 450 millimeters in development, but it will take some time to be used in industrial scale. And in research and development, you also have smaller diameters, like 4 inches, for instance. But the mainstream is 8 inches and 12 inches today. I'll talk a little bit about the schedule. So one thing that's interesting is the availability of those priority lots, that you can speed up the cycle time for engineering lots, for instance. And normally, for instance, if you have for a certain amount of masks, because if every process has, I don't know, a certain number of masks to be able to do all the steps necessary for the fabrication, it can take like 60 days for an engineering lot. And if you choose a priority lot by paying a premium, you can reduce this to 35 or 50 days, depending on the foundry and the technology, for the same number of masks. Of course, you have to pay a premium price for it, and it's not always available because you have to book in advance. And if every customer wants the priority lot, then there will not be a priority lot. Everybody will use the standard cycle time. So it's also, you have also to check with the foundry for the availability of such a priority or hot lots. After the IC fabrication, you sometimes need to post-process the wafer, and those there are 3 main steps in this post-processing phase, which are bumping, back grinding, and dicing. Bumping is usually required when you have to use a flip chip technique. For instance, in this figure here on the left, this is a photograph of a RFID chip that was flipped chipped on an inlay. And here you can see the marks of the bumps on the metal of the antenna. So these bumps are necessary or are required so that the flip chip can take place. Then you have to back grind the wafer. Back grinding is normally, if you're doing a MPW, for instance, you probably get all this done. You get the back grinding ready, you get the dicing. But if you are doing a multi-layer mask or a full mask set, you have to do it yourself, by yourself, or you have to have it done for you, not by the foundry, but for a third-party company that's specialized in those kind of things. And the back grinding is required to thin down the wafer to a thickness that is okay for the application, for how the chip the die is going to be assembled. Sometimes the package has a constraint in terms of height of the die, so you have to decrease the thickness. So you can decrease down to 350, 250, 150 microns, which is very standard. Then you can go also to thickness that are less standard, like 100 microns, 75, 50, even 50, 25. But of course, this will have increased cost because there is specific tooling required. For instance, in this figure here on the right, this is also for the same project here for this RFID. As we wanted to have the lowest cost possible. This was the main driving requirement for this chip. We would like to cram as many as possible dies on a wafer to increase the die count per wafer. So we wanted to reduce the streets, the dicing streets here, and hence here this is a test. It's not the final product, because here you have a big dicing street. But here is where the dicing took place. So this street is much smaller than this one. So this was a test with a stealth laser dicing. So these are the wafer post-processing steps, which are also necessary in the ASIC production. Then, after the post-processing of the wafer, you need to package the dies after it was bumped, if it's a flip chip, or if it's going to be used in a normal package. After back grinding and dicing, you need to package it, and you have several different types of packaging. You can use the bare die as it is. For instance, we have a case of a customer, very special application that didn't require any packaging at all, just the die itself. It's very, very interesting. Sometimes you need to flip chip, then you need to bump the before, so that you can use a flip chip technique to flip chip on the board, on the PCB, or on the substrate of a package. For instance, here on the right, we see a specific substrate that was developed for a BGA packaging for a high frequency ASIC. So this is also the package. Sometimes not just okay, let's send to the package house and have it packaged. Sometimes you have also to develop the substrate on which the package will be assembled. You have also chip on board techniques. Just use wire bondings to assemble the chip on the board, and then you cover with a resin or epoxy or something like that. And you have standard plastic package like QFN, or even ceramic packages for specific applications or for prototyping purpose, that sometimes the foundry or may have it already. And you have also wafer level packaging, where the packaging is done on wafer, which means that after you dice, you can already just flip chip, and you have the dies good to go. So this is the packaging, and after the packaging, we start the tests. And the tests, first of all, you have to bring the circuit up to life, and check some basic things like establish the communication with the chip in the first place, verify the nominal behavior, debug the characterization software, because you're not just waiting for the chip to come back from fabrication. Those 2 or 3 months you are using to develop all the characterization setup and software and hardware that is required for the lab tests. So once you have done this lab test, which also have their challenges, because you have to have the right good instruments to be able to make the measurement of some specific parameters. Sometimes if you don't have it in house, you have to outsource the tests, or count on a partnership with universities, for instance. Sometimes we do things like that. Sometimes we outsource some parts of the test, and the major part we do it in house. But of course, things like thermal analysis, that we don't have the thermal chamber. This is something that we normally outsource, and it's an important part of the tests. But then you have to develop the software that will communicate with the board. For instance, we use LabVIEW. We have to develop the software that goes with LabVIEW. We have to develop the test case, the test plan, to be able to have a report at the end that shows that the chip is according to specifications, which in fact is the silicon characterization part of the lab test. In the first place, we just brought it to life, and then we are going really to verify specific parameters of the chip. And then this is a very important part of the process, because although the simulation tools and the models that are developed by the foundries are very good, you only are sure that your design is working when you really sit down on the lab and you test the chip. This is very, very important. and we have in this phase to check all the parameters of the specification and to check if they are they are inside the minimum and maximum values of each and every parameter. So these are some examples. This is an example of our RFID measurement here. This is an example of an apparatus that we have to develop to be able to stabilize the temperature, to check the behavior of a temperature sensor. And this is a chip in the thermal chamber in a partner to do the temperature characterization. Sometimes after you characterize the chip in silicon, you maybe find a parameter that's out of specification, or you find a bug, a problem, a failure that you do not understand. When you understand, of course, you go back to the simulation, you check, you make some hypotheses, you test those hypotheses, and you check in simulation if why you find what's the root cause for that issue, for that problem. But sometimes you do not have a clue to where to search for the answer, and that's where a failure analysis can come in handy. There are some specific companies worldwide that do those kind of analysis. It's called failure analysis, and you can do like thermal analysis to check by the temperature of some specific areas of the chip to check for a current that is higher than expected that is running in some branches of the circuit. You can use light emission microscopy to check by the light response of the circuit if there's some a bad behavior. You can also use this XIVA analysis you put some laser signal on the chip, and this will make the circuit behave a little bit differently. And from this different behavior, you can that will impact on a change in the resistance of the circuit. You can force the circuit in a situation, and this will point areas that were affected by this. And then you can find out where the failure is, and then you go back to your simulation and you discover what's the root cause, and then you work on it. And sometimes you need to use FIB, which is a focused ion beam. And the FIB is useful when you have to remove a connection. For instance, you saw that you have a bad connection that was done, and you need just to cut that line. You just cut it to test if this solves the problem. Sometimes you need to make a new connection. Okay, I want to connect this node to another voltage, and then you just do with a FIB a new connection on the circuit. So although these techniques, the failure analysis and the FIB are very useful when you have bugs and when you need to discover or to determine a root cause that you're not able to determine without those techniques. And it's very important to be prepared for that, because if not, then you can run out of budget, for instance. So it's always good to know that those options are available and plan them up front. After that you test the chip and it's working according to the specifications, you need to guarantee, or at least have a good confidence that the parts that you're going to deliver in production to the customer are good. So you use a subset of the lab tests to do what we call the production test. You have to develop the program that will test automatically a wafer, or in a wafer level or in a package level, test some parameters that will inform to you that that part is okay. So there are fabrication problems that might happen. So the founder itself, when they fabricate a chip, there is a yield. So not 100% of the parts will be good. Sometimes because you have particles that falls on the wafer. So not 100% will be good. And the overall yield that also will include the design. So this is very important to have a good yield, so that you have most part of the dies on the wafer can be used in the product of your customer. But you have to guarantee that the customer is assembling good parts. So you cannot just give every one of the dies on the wafer to the customer. You have to just give to the customer, or to deliver to the customer, the good parts, which we call non-good dies. So the parts of this process are: you have to specify the tests, you have to develop the software for the test, you have to develop the hardware for the test, like probe cards, load boards. You have to define which test equipment you're going to be used. If there's some specific need for this test equipment, or if you can use the simplest one. Of course, the more complex the equipment, the more will cost the hour of the equipment, and the hour will impact in the final price of each unit of the ASIC. And you have the prober. When you have the wafer, you have a probe station to measure on wafer. And what's the output? In the case of a wafer level, you have probed wafers that can be inked or not. You're going to deliver this to the package house to be packaged, or a wafer map, where the package house can determine which are the good dies that must be assembled. And the package level test, the principle is the same, but you do the final tests, because you can also have problems on the package phase. So the wafer level will determine which parts are good, which dies are good, and the package level test will eliminate also problems on the package itself. And this is to illustrate a little bit the development of the production test. So you run the tests on a lot of samples, some wafers, and then you see this distribution of the parameters. You can use also corner wafers to be able to check also the limits of those parameters. And this is those values, those measurements are used to fine-tune the program, the test program, so that you can have a good program that can really only provide good non-dies to the next phase. And again, you have here the dies that are not good that will be marked. In general, the test program is developed with a partner. Chipus team will help the test house to develop this test program. The test houses for high volume are mainly in Asia. Of course, we have test houses in the United States, in Europe, and a lot of places. But in Asia are the ones for very high volume. And just to have an idea, in Asia, small volume is considered, for instance, a decent small volume is considered 200 wafers per month, which is, if you talk about 1 millimeter by 1 millimeter die at 90% yield for a 8-inch wafer, it will be in the order of 50 million units per year. So this is a small, decent volume for Asia standards, for instance. And to decrease the production test will impact on the final chip price. So you want to reduce the test time as much as possible. So here we're talking about a few seconds and not more than that. Of course, depending if it's a high-end or a low-end product, you can afford having a more complex or a less complex test. Then you can go to the qualification. The qualification is the last part of the test. The first, the lab tests shows to you that the ASIC is working in performance according to the specifications. The production test will show to you which dies you have to discard, which mounted dies you have to discard, and only deliver good dies to the customer. And the qualification will verify the reliability, mainly the reliability of your ASIC in terms of fabrication, design, and packaging. And you have standards for it, like the JEDEC standards that define for commercial and industrial applications. You have also some standards from the automotive. It's not AEQ here, sorry, it's ASIC, Automotive Electronics Council, that define standards for the qualification of products that will be used in the automotive market. You have also ongoing reliability tests, or T, that you do during production, so that you verify during the production of that circuit that you are able, that everything is okay in terms of robustness and so on. And those kind of tests use, like, sometimes high temperature to stress the chip and emulate, like you test 1,000 hours at 125 degrees. This means that this probably means that you it can be translated in like 9 years of operation, for instance, of the circuit. So you want to know if your circuit will resist such amount of years in the field. And some types of tests that are used to qualify here are early life failure rates, and also some storage tests. And ESD and matchup is also important to be done. Sometimes the foundry also guarantees that by design in the pads that they provide with the technology. But sometimes it's important also to do ESD and the chip. It will depend a lot on the customer requirements of this. And some environment tests, like temperature cycling and humidity, are also important. This is the qualification phase, and then you are good to go to production. And in production, you have to take all the previous phases and use that in an efficient way to deliver dies, deliver ASICs in volume production. You have a lot of logistics associated to that. The semiconductor supply chain is global. You have, for instance, you can design the chip in Brazil, fabricate it in Germany, then do the post-processing phase in Asia, and then deliver to the customer in the United States, for instance. So the wafer will travel across the globe, from start to end of the ASIC flow. So you have to go to the foundry, to the test house, to the wafer sort, and the wafer post-processing, the packaging, the final test, and to the customer, and then all this, there is shipping, physical shipping involved. Then you have order placement, inventory control. You have to make international payments. You have to comply to customs requirements, fill forms, obtain clearance from the customs. You have to understand about import-export terms and taxes. You have to support the customer during the production when the product is in the field, and have reports to monitor yield performance. Also the ORT that I said before, and this back and forth. And of course, today we have this COVID-19 situation. We don't know how long it will last. We hope not much more than the already 3 months that we are on this. But it has indeed affected the supply chain, because several countries faced lockdown. And so what we observed is some shortage in supplies, and also an impact on the time, so increased time to deliver some of the services. So this means that you have to be better organized, plan ahead to avoid those kind of things. So with the arriving to production, so we started on the concept, and we arrived finally in the production, and we saw some challenges on each of the phases of this ASIC flow. Of course, we have partners for everything, from design to production. We do the design ourselves, but sometimes we also have partners for it. But we have mainly partners for the supply chain after the fabrication. So the fabrication, of course, we don't do that. It's a family ASIC business. And then also the tests, we help the tests in the development of the tests, and the lab tests we do ourselves. But then the wafer post-processing, back drying, dicing, bumping, packaging, it's all done by partners. And this is very important to have a very good, very well established supply chain to deliver working and successful ASIC at the end. So with this, I finished my presentation. I'd like to thank you for your patience until here to listen to this. And now Heider is joining me to answer the question. And it's already almost midnight in Switzerland. So I will take 15 minutes to answer the questions. And then Heider will help me for the beginning from now, but he can take more questions after those 15 minutes. So please feel free to ask us as many questions as you have, and we'll try to give a good response, or at least the answers that we have for them. So thank you again, Professor Ricardo Reis, and now we open for questions.
So thank you very much, Paulo. So we have here several questions. So first one by Salvador Jimenez from FEI, São Paulo. What is the main bottleneck currently in terms of the time to launch a new SoC?
What is the main bottleneck?
Yeah.
I think there are bottlenecks everywhere. It depends a lot on the type of the SoC. There can be a bottleneck, a technical bottleneck, so depending on the complexity. But there can be, today, as I said, the COVID-19, there can be a schedule constraint that can be also a bottleneck. It really depends a lot, because an SoC can be very complex and you can have bottleneck everywhere. I think that would be the best answer that I could give. Or maybe going a little bit further, if you think about an SoC, you're probably thinking about a heavy digital part in it, like a processor. So maybe the bottleneck can be cost. For instance, if you have to use a very fine technology like 7 nanometers, so you have a very high cost in terms of NRE to buy the mask sets and also the wafer. So this can be the biggest bottleneck for a big SoC, for instance.
Okay, another question also by Salvador Jimenez. Does Chipus use some EDA optimization tool to design analog blocks? Would you please comment about this?
We use and we have used more in the past Moneda tools for optimization. I think Heider can answer this better than I do, because he was involved and is still involved on that. So Heider, can you take that question?
Sure. So currently we don't use that so much, mainly because we don't see much. I mean, there is value to it, but we could not fit it inside our flow, inside our design flow. So currently we don't use that, but we have the expertise, and there are some kinds of designs that you can benefit from it. So in certain places it's beneficial, but we don't use that nowadays.
Okay, thank you. So Another question from Juan Pablo Brito from CETEC. I'd like to know if you add the results of the statistical measurements in the technical documentation of your IPs.
The statistical, yes, we normally add the simulation results for the statistical measurements. For the measurement itself, then in the silicon characterization, then it really depends on how many samples we have tested, and if it went in production, then we have the statistical measurement for the wafers. If not, we have just the lab statistics, which are not very good in terms of statistics because it's a limited amount of samples that we measure. So for that, we trust on all those steps that I have mentioned. So first of all, the lab characterization. So we need to guarantee that for the samples that we measure, they are inside the specs. And then in production, for the test and the qualification, then we will guarantee the rest. And of course, the silicon characterization goes together with the simulation results, because you're not able to do a Six Sigma measurement. You need a horrible amount of samples, but you can do that in simulation. So you have to use the simulation at your benefit, but you have to use it wisely, and you have to use the lab test to test what you're able to test, and also corner wafers and things like that. So it really depends on how many samples you have tested to be sure if the measurement, the silicon result that you have provides significant statistic information, or if we take that from simulation and supported by simulation and by the limited samples that we have in characterization, we believe that this is enough to say that the circuit or the parameter is according to the specs, even between minimum and maximum that was defined.
Okay, so we have now more 14 questions. So the next two are done by Fernando Herman. So the two questions are about EDA tools used during the design process. So first one, could you please talk a little bit about the EDA tools license price and how Chipus managed this with the customers? And the second one, how much the cost of the license represents from the total development and fabrication chip costs?
Oof. That's a hard question. First of all, because we have an NDA with the EDA vendors and we cannot reveal the price. This is a negotiation that we have with them. Every company negotiates the EDA tools price, so we are not allowed to say the price that we pay. So it depends on the vendors also. Today we have access to the three biggest EDA vendors. We have a flow that's a mixed flow, so we can take the advantage of each of them for depending on the circuit or on the technology, if there's PDK available for all of them or not. So unfortunately, I cannot answer the first question. And the second question, how much it represents, I don't know. It's difficult to say because this is we have to compare to the NRE of an ASIC, for instance. How much the EDA represents to that? I don't know. If I answer that, you make the reverse calculation and you know how much we pay. So unfortunately, I cannot say. Well, the only thing that I can say is that EDA is representative. It's not even if we have very good negotiations, because we still We have a good negotiation in place with all the customers, with all the vendors, but it's still it's representative. So you cannot neglect that. So that's what I can answer about that. I'm sorry.
Okay, another question by Juan Brito. Of all the flow you have shown, which part is made internally by Chipus and which is subcontracted?
So I think I answered that on the concluding slide, but I will repeat. So the design, we do everything internally. Sometimes we have partners to do part of it, some layouts, for instance, depending on the availability of internal resources. So sometimes we do that, but in general, 95% of the case we do everything in terms of specification and design internally. Lab tests we do also internally, but sometimes we don't have all the equipment. The equipments are expensive, and we need to use partners to do the lab tests. And the rest is we manage the supply chain, but we don't do that ourselves. We will participate on every phase, but like the production test, we will help in the development of the test, but we will not do that ourselves. So it's mainly the design and the lab tests that are done inside Chipus.
Okay, so next one is done by Fabrício Alcalde. How do you start a silicon IP company? Do you make a generic IP portfolio and then look for clients? Do you need support from another institutions like universities?
So that's a good question. Thank you. All of them are good, in fact, but it goes back, makes me go back in time a little bit when we started Chipus in 2009, and I don't know how you begin a silicon IP company today, but I can tell how we began ours. And we began ours more or less, as you said. We had a partnership. We developed a partnership with a foundry. At the time, it was L Foundry in Germany, in Landshut. And we developed a portfolio of IPs. We did a test chip with IPs that we had expertise to design from previous experiences. And so we did a test chip of low power, low voltage IPs, ADCs, power management blocks, power management units, touch sensors and things like that. And this was our business card to go to talk to customers. And because when you're starting, you have to start somewhere and somehow. So for us was having this test chip. So we know how to do this. We know how to have this expertise to do those kind of things. And here is the proof. And then we show the silicon proven IPs that we had done. And of course, we had also our contacts that we had in the past that were very important. Also people that trusted on us. And the first contracts came like this with trust. And it continues to be like this today. The trust in this market is very important. So when you do a good job, the word will pass on, and more customers will come to you. So the most important thing when you start an IP company is doing a good job from start.
Okay. So we still have 12 questions, and then who wants to do another question? So please do now, because we are going to close for new questions in, let's say, 1 or 2 minutes. So next question is from Professor Paulo Aguirre from Unipampa. How is the average total ASIC development time from the customer first contact to the delivered ASIC?
It really depends on lots of things, but for instance, the RFQ process itself, from when we receive a request to the start of the project, can take from 2 months to 1 year. Normally take 3 to 6 months, this process. So this already consumes a lot of the time just to start a project from a customer requirement. And then the rest will really depend on the complexity of the chip. If we have IPs that can be reused, the schedule of the foundry, how many runs we'll need to do this. Sometimes we do it in only 1 run and maybe use a metal fix to correct or to improve something on the circuit. Sometimes if it's a very new or very challenging design, we probably want to have 2 or 3 runs. It really depends. And all those, if you think that 1 run takes 3 to 4 months or 2 to 4 months, you add this up, and then you can have from when the request comes to us until you deliver the design, you can have from 1 year to 2 or 3 years. It depends a lot on the complexity.
Okay, thank you. So another question by Juan Brito. How many customers Chipus have in Brazil?
In Brazil, we have 2 customers.
Okay, so next question by Professor Jacob Swart from IMEC in Brazil. How is the market for ASIC service along these 11 years? Is there a shortage of ASIC design house or an excess?
Hi, Professor Jacobus. Thank you for watching the talk. Maybe you also know a little a part of this answer, because you're also on this business in IMEC. But I think for the moment being, I don't think there is excess or shortage, at least from the amount of business that come to us and that we are able to close. So for us, we cannot complain, neither for having a lot and not being able to answer to those, neither complain that we have too few and then want more. So maybe I can also pass the word to Heider, who is our technical sales manager, and he can complement on that.
Hello, Jacobus. Nice talking to you by text. So, I agree with Paulo. I don't think there is too few or too many. I think people are, there is competition, that's for sure. There are competent ASIC houses out there. But I don't think there is, I don't think it's reaching a point that it's becoming negative. Okay, that's my feeling.
Okay, so next question by Christoph Hermann. First of all, thank you for a great presentation. By the way, there is a lot of message congratulating you for the excellent talk. So I have really enjoyed it. Could you please tell something more, if possible, about time proportions between the mentioned ASIC fabrication steps?
First of all, thanks a lot for the compliments and for also conveying the message that there are a lot of compliments there. I haven't seen them because I'm not reading the text. I'm just listening to the questions that Professor Ricardo Reis conveys to me. So thanks a lot for that. I'm really happy that the talk is useful and interesting. I have to also thank everybody at Chipus that helped me with this talk, because all that I presented here is a teamwork. It's not something that is on me. It's all is about all the people that we have on the background. So I extend the compliments to my team. and then I have to ask Professor Ricardo Reis to repeat the last part of the question because I didn't get it.
Yeah. Could you please tell something more, if possible, about time proportions between the mentioned ASIC fabrication steps?
The time proportion between the main ASIC fabrication steps. I'm not sure if I... The mentioned fabrication steps. I'll try to answer that, although I haven't completely understood the question. So the fabrication steps, if I understand fabrication as I explained, there is only one. That's the IC fabrication, the wafer fabrication. Of course, the wafer fabrication itself has several steps, several masks, and it's a very complex subject by itself. But if we consider the fabrication as the whole thing, after the GDS delivery to the foundry until you have the packaged parts, then I don't know, you can have like considering engineering lots from a dedicated mask. You have, let's consider 2 months for that. Then you probably have 1 month for the rest. So it would be, I don't know, more or less something like that. So the bumping can be very quick. The back grinding dicing too, and the packaging too. Of course, this has to be done previously. Have all the tooling ready for that. Not something that you now I have to do a package. So let's do the packaging now. You have to have done this before. So everything is already planned and scheduled and booked. So then you just place the order, and you have more or less, I think, 50% of the time, or a little bit more. 60% will be the wafer fabrication, and maybe 40% will be the rest, including shipping and everything. This is I don't know. It's not a precise answer. It's more or less something like that.
Okay, thank you. Question by Sebastian Passos from Buenos Aires, Argentina. What kind of silicon issues have you tracked using thermal imaging light emission? Circuit, power issues, analog figure of merit of specs, and so on.
So for that particular image that I showed in this slide, let me see if I can get back to it. So here we had at the end with the light emission, we have discovered a latch-up problem. It showed that there was some kind of latch-up in the circuit, that we had a problem with the supply voltage that suddenly dropped, and we didn't understand why. And this kind of failure analysis showed to us that it was due to a latch-up problem. So we got back to the circuit. We detected where was the latch-up, and we corrected it. So this was the case. For the thermal analysis here, I don't think we had a very clear answer. The images didn't show something that we could, for this specific project, didn't show something that we could, okay, this is the problem. It just gave us more insights, more time to think about it. After all, we were able to determine the root cause of the problem, but it was not the image, the thermal analysis itself, that gave us the answer.
So now a question by Brito Filho. So congratulations for your presentation. Did you tape out any chip using fabless design flow with open source tools? How do you compare with the commercial ones?
That's a good question. Fabless, there's a very interesting news that came these days, that they are partnering with Google and the Skywater foundry to release a PDK and you can fabricate, I think, for free some prototypes. So we have discussed a lot with the fabless in the past. We have even started designing something with them and proposing a challenge, as they call, and it's very exciting what they are proposing. I like it a lot, but we didn't go until the end and really design a complete circuit with them. At the time, it was, I don't know, 5 years ago or 4 years ago, don't remember. I remember that we found that the platform they used was kind of slow, because that was our impression. But I know when I talked to Mohammed at the time, that's from Fabless, they had improved a lot this tool. So I'm sure that they have something very good today, and hopefully this will help to democratize IC design. So more people know what it means. And when more people know what IC design means, it becomes much easier to have business, to increase the business volume with that. It's like open source software. The open source software did not jeopardize or did not ended with the commercial software. I think there's place for open source or for all those kinds of things in the IC business, like Sci5 is also doing with the RISC-V. So all those things are very welcome, and it's very good to be in contact with those companies, and it's very good all those initiatives to democratize the semiconductor business.
Another question by Douglas Santo that is related to this one. Any thoughts on the SkyWater open source PDK?
I will give that to Heider. He's the one that knows better SkyWater. He has more contact with them. We have already discussed a little bit with SkyWater in the past. So Heider, can you give some hints for us here?
So as far as I know about what they do, it makes sense for them to have an open source PDK because they are a very custom foundry, right? You can make some devices really customized to you. And once you do not have that, you have to make things layer by layer. It can become very, very annoying to implement the layout. So if you want to have something, that's not the ordinary P cells that the foundry provides you, it really makes sense to have an open source PDK.
Okay, so next question by Alfredo Arnaud from Montevideo, Uruguay. Thanks for the presentation. What is a realistic spec to silicon time for a single design in industry, from specifications ready to first lab tests using a dedicated run?
Thanks for the question. I think I would say 6 months, just to be very, for an example, from frozen specs to lab tests, you consider 2 months of fabrication and 4 months of design. 6 months, I think, would be a good number. But of course, depends on complex, depends on a lot of things. But I think that's a good number to have in mind.
So another question by Sebastian Passos from Argentina. How commercially viable would you consider a design house to be where most product level processing, foundry package testing is outsourced?
This is sorry. As time is advancing here, this would be the last question that I will answer, and then I will give to Heider the floor so that he can answer all other questions. He's very well positioned to answer that. But just to answer this last question, can you, I'm not sure if I understood. The question is how feasible or how viable I think a design house is. And then I didn't understand the rest about the other things. Can you repeat the last part of the question, Professor Hayes?
Yes, I did not understood well also, but so the first, so the whole question was how commercially viable would you consider a design house to be where most product level processing, foundry package testing is outsourced?
How viable, how commercially viable is a design house to be where all the rest of the process, the back-end process is done, like a design house in Asia? Is that what you understood also?
So maybe Sebastian can clarify the question, and then I can do it again. Okay, Sebastian. So we go to the next question. So Professor André Luiz Aita from Fédérale University of Santa Maria. So thank you again for the presentation. So IC design is not nowadays one-man army thing, it seems. In your opinion, what is the minimum number of designers to cover all the design flow steps?
Okay. Hi, Professor Aita. Thanks for watching the talk. So that's a good but also complicated question to answer. Yes, it's not a one-man army, although I know one-man arms that exist that can do the whole thing, but it's very special. I think again, it depends a lot on the complexity. It depends on the tools. It depends on a lot of things, but. I don't know, I think to do the whole design flow, if you consider digital, analog, and you have a very tight schedule, you probably need, I don't know, 5 to 10 people. But again, if you have one very good guy and you have a lot of time, then you can do it alone. But in general, I would say that you have 5 to 10 people can do the job. So this was the last question that I answered. I'd like to thanks again Professor Ricardo Hayes for inviting us. Heider will continue to answer the question, so please stay and continue until it's possible. Professor Hayes will stop the questions when the time comes.
We have two questions.
Two questions.
Qualification by Sebastian.
Okay, so I'll stay for the two questions.
So the next two questions. First one is.
But I'll leave to Heider answer, and I will complement if I have something to complement.
Reality Roberto Panipucci is saying thank you for the great presentation. And the question, how do you see CTI in Campinas supporting the development of more design houses now that we have a technical park?
Is that true, Paulo?
Yeah, you can answer, and I can complement.
You're the operation guys, so I think it's best if you.
Okay, if you want to complement, then you complement. So thanks, Heider. Thanks, Panipucci, for the question, for watching the talk. Thanks for the compliment. I think CTI is it's very important for Brazil. We have used CTI in the past a lot for packaging, mainly for chip on board packaging, but also for some other kind of packaging. And in the beginning, when I was still studying microelectronics, CTI was also responsible for the multi-project program of FAPESP. So without those kind of things, it will be very, very difficult to study microelectronics in Brazil. So I think CTI has a very, at least from my personal education, it was very important. And CTI has a very, also a past that's very important in IC design. Nowadays, unfortunately, I'm not so aware about the technical part. Maybe we could talk about this later. I don't know if Heider can help me with that. But I think what the design houses in Brazil they need today is an extension of the lab, so more equipment to be done, to be used to characterize silicon samples. Needs ATE for test development. I know that CTI has a tester, so like Teradyne or things like that. So access to those kind of equipment that are expensive is very important. The packaging know-how that CTI has. So for prototyping, packaging is it's always a headache in Brazil, because we have the custom problems that we know how to handle it after 10 years. But it's of course still difficult. It's difficult in terms of cost, in terms of bureaucracy. So if CTI does those kind of things in the prototyping phase, would be very, very interesting for this initial development. So packaging, testing, and also the production test, development of production tests. So those kind of things are very interesting. I'm not sure if CTI has also failure analysis equipment, and FIB, I think they have something in the past, I don't remember. So all of those things that we do abroad today, it would be very, very good if we could do at CTI. So that's, I think CTI could support the design houses with all those steps. I'm not sure what the technical part is today, but I'm curious to know if we could use CTI for our prototyping, for instance.
Okay, thank you. So clarifying here a little bit the question of Sebastian Passos from Argentina. So in reality, his question is related to how can, let's say, be viable design house where there is no foundry related to. So,
okay, so if a design house is viable without the ecosystem, local ecosystem, is that
foundry ecosystem? Yeah.
Yeah, so of course, like if you are in Taiwan, you are a design house in Taiwan, you have the foundry, all the wafer post-processing, packaging, testing, everything. It's much easier to do the job. There's no doubt about that. But I think we are an example of viability of design house. Although we have CETEC in Brazil, and we had also Unitec. The process that we used were never the process that they could provide to us. So we're never able to use those foundries. So we always used foundries abroad in Europe, in Asia, and that works. As I said, one of those slides, the supply chain is global. Of course, there's a trend now with the COVID situation, the United States wars China, to try to get back those capacities to the United States, for instance. It's still a global market, so you can be, in terms of design, you can be anywhere in the world, and you are able to, and if you have a good process flow, you have a good team, then you have a potentially viable business.
So last question by Augusto Neusling from Cadence, England. Would you like to expose your opinion about the possible future of CETEC? Was and how CETEC was important for the Chipus creation and development?
That's a delicate matter. The CETEC is it's very important for Brazil because it raises the awareness about semiconductor. It increases the awareness about semiconductor. So as many as companies and institutes working with semiconductor, microelectronics, IC design we have in Brazil, the better the awareness that we have in Brazil, so the best will be for the ecosystem in terms of investment, private, governmental, and it's for sure very important. And the future of CETEC, I don't know. I hopefully they will find a way out of this problem, of this issue. I know that there are very competent and skillful designers and managers and people there, and the process people and everything. There was a lot of effort and love built around CETEC. Of course, there were problems, and they have to be solved. So hopefully, the people in charge will be intelligent to find a good solution for CETEC, and I believe that they will do with the help of the community, the semiconductor community, and the local government that I think is very interested in this. The local, I mean, the state of Rio Grande do Sul government, so, and the Porto Alegre municipality. So hopefully this will end well. Let's see. Then the future will tell us. I don't have a crystal ball. Fortunately, I don't have. And the importance that CETEC has to Chipus. First of all, Murilo, our CEO, was in CETEC before founding Chipus with me. So he brought a lot of know-how from his time in CETEC, from the period that he was there managing the analog group. So this is the first thing about the CETEC importance for Chipus. If there was no CETEC, probably Murilo would have stayed in Portugal, in Chip Idea, and we don't know where he would be today. Maybe, I don't know. We cannot go back in time and change things. So this is difficult to tell, but this is the first thing. And secondly, the fact of CETEC being in Brazil, this is the awareness creation. There are more industry knowing about microelectronics and semiconductors, so there are more business around. We have also possibility to discuss some potential partnerships with CETEC. We have not been able to make them concrete for some reason, but not there was no bad will in there. It just didn't happen, as did not happen with other companies and institutions either. But I think CETEC is important for Chipus because it increases the ecosystem today, because it increases the ecosystem. It keeps a talented workforce in semiconductor in Brazil, and this is very, very important for everybody and for the increasing semiconductor ecosystem in Brazil. So let's hope for the better.
So thank you very much again, Paulo, to stay so late in the night to give us this nice talk, and also Heider to participate in the answering questions. Thank you to everybody that attended this talk. So thank you again, Paulo and Heider. Thank you very much.
Thanks, Professor Reis. Thanks, everybody, for the questions and for being here for the talk today. Thank you. Thanks, Heider.
I also would like to add that all these talks, we have an important participation of Professor Rafael Brum, that is the main responsible for all the video conference system that we are using and broadcasting in YouTube. So thank you, Rafael.
Thank you, everyone. Good evening, and see you on Friday.
See you. Bye-bye. Good night. Good night.
Bye-bye. Thank you.
Bye, guys.
Bye. Ciao.